All right, welcome. This is the second of the equilibrium videos. In this video, I'm going to be talking about calculating K from concentration information, and in that context, I'm going to be introducing you to something called an ICE chart, and then we'll look at how we can do this type of problem when we have Ka, Kb, and Ksp problems, so that hopefully you realize that there's definitely a pattern here, and we're essentially doing the same thing in these different types of situations. So this is the second of our primary topics on equilibrium. The first was writing equilibrium expressions. Now we've moved on to calculation. So we're calculating the value of K when we've been given concentration. That's what this is all going to focus on. Now, there's a general strategy for calculating K from concentration that's shown on this slide. So this is our strategy slide. How do you do this type of problem? First up, you determine initial and equilibrium concentrations where you can, basically from the information that's been given in the problem. You try to organize it, like, hey, what's the initial, what's the equilibrium? Then you determine the change that had to have happened between the initial concentration and the equilibrium concentration for your knowns. Basically, from the numbers in the problem, work out the change between initial and equilibrium based on what they've given you. Then you're going to use that change that you determined for one chemical species and apply it to the change for the other chemical species that are in the reaction using stoichiometry, using ratios. You know that if everything's in a 1-to-1, that if one reactant went down by a certain amount, the other reactant must have gone down by the same amount. That's that idea. Then you will simply calculate the equilibrium concentrations for based on those changes that you worked out. So it's like you work out the change and then you simply apply the change to calculate equilibrium concentrations, and then you simply plug the equilibrium concentrations that you determined into a K expression, and that allows you to solve for the value of K. In other words, this whole strategy that is laid out on this slide is essentially saying use an ICE chart. An ICE will stand for initial, change, and equilibrium. ICE, and in that order, initial, change, and equilibrium. So to show you what I mean, we have a simple problem here. For the reaction shown below, calculate the value of K for reactions starting with 1.000 molar N2 and 1.000 molar H2 produces 0.157 molar NH3 at equilibrium. I'm going to solve this with an ICE chart. So I have the balanced chemical equation, and I'm simply, to sort of show you how I'm filling this in, I'm going to write three sort of rows, I, C, and E, initial concentration. So we're going to start with initial concentrations. Essentially, we're going to think about what information the problem gives us. And the problem tells us that we're starting with, so that's initial, 1 molar N2 and 1 molar H2. So I'm going to fill that in for both the N2 and the H2. I know the problem tells me that I'm starting with 1 molar N2 and 1 molar H2. Great. And then it says it produces 0.157 molar NH3 at equilibrium. Ooh, well, that's a big one. That's not initial. That's at equilibrium. The problem literally tells me that at equilibrium, we have 0.0157 molar NH3. So in the equilibrium column, I'm going to fill that in for the NH3. Now, those are the three numbers that the problem gives me explicitly, but those aren't enough numbers to fill in the rest of the ICE chart. So then the key is recognizing that the problem actually implicitly gives you a fourth number. And the fourth number is the initial concentration of the NH3. Think about this. When you're doing a chemical reaction, you start with reactants. You don't start with products. The implicit number here is 0 molar. You're not starting with any ammonia. The problem, in fact, says that we're only starting with nitrogen and hydrogen. So you do actually know. The problem doesn't have to tell you this because they think that you can, figure it out, that you're not starting with any products. You're only starting with reactants. This is a big thing in equilibrium. Unless the problem specifically tells you that you're starting with a certain amount of product, you are starting with 0 product. Unless there is specific information about starting with an initial amount of ammonia, you know you're starting with 0 product in every problem, in every case. So we know that we have 0 molar product. That's key. Now we can fill out the change row. Now, which thing do we have the most information about? We have the most information about the ammonia because we have the initial and we have the equilibrium. So therefore, we know that it must have changed by 0.157. But now, did it go up or did it go down? Well, it went from 0 to 2.157, so you know it increased by that much. So I am going to write a plus. Now, this should make sense because products They're products. They're being produced. So you're going to create them. You add to your amount of products every time. You're increasing your amount of products. Versus reactants, they decrease, they get used up. So our arithmetical function for our reactants for the change column is actually going to be minus. So I'm going to write that in right now. So I figured out the change for the ammonia. Now I'm going to use stoichiometry to figure out what the change for the nitrogen and the hydrogen must have been. So this is where the coefficients are going to come into play. So the change for the nitrogen is going to be 1/2 of the change for the ammonia, 1/2 of 0.157. Because the way I figured that out is I essentially said if the change for the NH3 is 0.157, this is NH3, then I'm just using my ratios in essentially a t-chart that says that, well, you know, okay, 2 moles of ammonia come from 1 mole of nitrogen. So the change for the nitrogen must have been 1/2. There's that 1/2. That's where that 1/2 came from. And then similarly for the hydrogen, now the change is going to be minus 3/2 of 0.157. And this is worked out the exact same way. The reason I know it's 3/2 is because, okay, I'm going to take the 0.157, and this is NH3, and then I'm simply going to use my mole ratios, and 2 moles of NH3 come from 3 moles of H2. So, you know, there's my 3/2. That's going to be the change in the hydrogen, and that's how we're working that out. So that's what I say when I mean we're using stoichiometry to get the change for everything else. Okay, now I can actually calculate the equilibrium concentrations by simply doing the math that I've set up in my ice chart. I said that we're starting at 1 molar for nitrogen, and then we're going to lose 1/2 of 0.157. So, okay, that's just calculating it. And the equilibrium concentration winds up being 0.9215 molar for the nitrogen. For the hydrogen, again, do the same thing. 1 minus 3/2 of 0.157 will give us 0.7645 molar. So that's just math. You're just doing the math that you said to do. Now you have an ice chart filled out. Yay! Now we can go back and look at what the problem is asking us for. It's asking us for the value of K. We have worked out the equilibrium concentrations. What we're going to do now is write the equilibrium expression for this reaction. So it's products over reactants raised to their coefficients. So it's NH3 squared over N2 times H2 cubed. This is an expression. It's a formula. You can plug stuff in and solve for the unknown, and that is precisely what we're going to do now. We have the equilibrium concentrations for all 3 of these things, so we are just going to plug and chug and solve for the value of K. So we said that we have to take the NH3 concentration, which is 0.157 molar, and square it. Great. And then we're going to divide by the N2 concentration, which is 0.9215. Again, we only use equilibrium concentrations in an equilibrium expression. And then the H2 concentration, which is 0.7645 molar cubed. And then you simply solve. That's all you do. You solve and you get a value. So when I solve this, I get a value of 0.0. I think I can't read my writing. I think that's a 599. I hope it is. But I think you get the idea. And this is equal to K. This is K. Remember, K has no units. It's a ratio. It's a ratio of products to reactants. So this ratio, because it's less than 1, it is telling me that there are more reactants than products at equilibrium, which I can actually see from the equilibrium concentrations. And there you go. That's the process. That's the procedure. Fill in an ice chart. Initial, change, equilibrium. Products start at 0. Figure out the change for one species. Use stoich to apply that change to the other species. Plug it into an equilibrium expression and solve. In fact, this is going to be our strategy for almost every single equilibrium calculation problem we see. This is our strategy you're going to see me reference again and again and again. If you don't know what to do in an equilibrium problem, if you do these steps, you'll probably get pretty far in it, if not solve it completely. Write a reaction to describe the system. If a reaction has not been given to you in an equilibrium problem, then write a reaction. How do you know which reaction to write? That's a good question. Look at what they're asking for. If they're asking for Ka or they give you Ka, then you write a Ka reaction. You write an acid dissociation reaction. If they're asking for Kb or they give you Kb, write a Kb dissociation reaction. If they're asking for Ksp or they give you Ksp, then you write a Ksp dissociation reaction. That's the reaction that you write. Then once you've written that reaction, you fill in an ice chart as best you can. You get as far, you try to complete that sucker. Then once you've filled in the ice chart, you write the K expression and plug in your values and you solve. You solve for whatever it is they're asking about. That is our basic strategy. Reaction, ice chart, expression. Reaction, ice chart, expression. You're going to hear me say that a lot. So what's different about Ka? How would you see this type of problem in a Ka situation, this asking for Ka from concentration information? So an example is the pH of a 0.1 molar solution of formic acid was measured to be 2.38 at 25 degrees Celsius. Calculate Ka for formic acid at this temperature. Remember, pH is a comment on concentration, right? So when we see this, we know that we have the hydrogen ion concentration. It's not equal to H+, but we can get H+ from pH. A couple key points about this. When you have this situation, the given pH is the equilibrium pH, not the initial pH. Because sort of the idea is that when you start with your weak acid and there's no water present, meaning it has not yet dissociated at all, there is no H+ there. When you place it in water and it dissociates a bit, that H+ is actually the equilibrium H+. That H+ was not present. When you started, all you had was this, like that was your initial. So H+ is actually a product. So we know that the pH is the equilibrium concentration. It will get us that. So that's a big thing. That pH is not the initial concentration of H+, it's the equilibrium concentration of H+. pH allows you to calculate H+. So you'll have to calculate that, but that should be easy for us right now. If you don't have a reaction written, like we actually don't in this particular problem, write a Ka dissociation equation for the formic acid. So HCHO2 goes to H+ plus CHO2 minus, and then you're just going to set up a Ka expression. You're going to fill in the ice chart for that Ka reaction that you wrote, and then go to a Ka expression, plug, solve. What's different about Kb? Not that much. It's basically the same as a Ka problem with one very small tweak to it. So now we have the pH of a 0.2 molar solution of ammonia was measured to be 11.28 at 25 degrees Celsius. Calculate Kb for ammonia. Same thing, same idea. The given pH is the equilibrium pH, not initial. Always. This is always going to be the case. Unless the problem says the initial pH, like they would have to use that word initial. If they don't, then it's equilibrium. The only tweak between this and Ka is that they gave you pH, but we don't want pH for Kb, because for Kb we're going to have hydroxide, not H+ concentration. So, okay, take pH, get POH, and then use the hydroxide concentration in your ice chart. I mean, that's it. That's the difference. So there's one tiny different step. So our strategy is going to be the same as before. Write a Kb dissociation equation. That's the reaction that you want to write. Like one was not given here in this problem. You'd want to write the NH3 plus H2O goes to OH minus plus NH4 plus. Set up a Kb expression. Fill in the ice chart for the base dissociation reaction that you wrote. And go to the Kb expression and plug in. Now, a little note here. A lot of nitrogen compounds like ammonia or CH3NH2, they tend to be weak bases. So this is just kind of a thing to look for. If you notice that you have, excuse me, a nitrogen compound like this with maybe even it looks like a lot of H's and a lot of C's, it's probably going to be a weak base. And you'll want to write it as, attracting a proton rather than donating a proton. What's different about a KSP problem? In an example problem here, that's shown for you. It says a saturated solution of silver chromate is prepared where the solubility of Ag plus is 1.3 times 10 to the minus 4th molar. Calculate KSP, assuming the system is at equilibrium. Okay, couple key points, and one that I neglected to include in the type on this slide, unfortunately. Saturated. This is a big one for KSP problems. This is code for equilibrium. So when you see the KSP problem say that it's saturated, that is telling you that it's at equilibrium. So in this problem right here, when it says the solubility, the saturated solution has the solubility of Ag plus to be 1.3 times 10 to the minus 4th molar, that actually means because this is the saturated concentration, that means that this is the equilibrium concentration. So that's a big, big thing. If it says saturated, that means we're at equilibrium. So if this is the saturated concentration, then that means that's the equilibrium concentration. On KSP problem, you want to write a KSP dissociation reaction. So this one we'd write Ag2 CrO4 goes to 2Ag plus CrO4 2 minus. Solubility is not KSP. It's not the same thing. Solubility, if it asks for solubility or it gives you solubility, that's molarity. Solubility is molarity. How many moles per liter dissolved? How many moles per liter went into solution? So solubility is the molarity of an ion. The phrase molar solubility is often one that we see in this type of problem. I don't know why they use a different term, because all it means is molarity. So know that when you see that phrase, if you see that phrase, molar solubility, it just means molarity. It's just telling you the concentration of the ion. That's it. Watch your ratios. Quite often, the ions that are in KSP problems are not in 1-to-1-to-1 ratios. Typically, in the acid-base problems we're going to be doing, yeah, everything is nice, it's 1-to-1-to-1. Usually not the case in KSP. We notice in this one, for example, it's a 2-to-1 ratio. So the change for the silver is going to be twice the change for the chromate. So make sure you're watching your stoich on this type of problem. Be mindful of units. Quite often, grams per liter could be given to you as the solubility, as the saturated solubility. You cannot take that number and plug it into the ice chart. You have to use molarity in an ice chart because, remember, we're using the ice chart to get the equilibrium concentrations to use then in the K expression. So we need molarity in the ice chart. So simply convert first and then do your work with the ice chart. And that's really it. Those are the fundamental differences. So tomorrow you're going to be seeing essentially all these types of problems, and you're using this strategy for a Ka problem, for a Kb problem, for a KSP problem.